In this video lesson, we're going to cover how to do logarithmic differentiation. So when will we use this? Well, we've done functions where we have a base that's a variable raised to some sort of power, and for those we just use the power rule. We now have looked at ones where we have a base that is some sort of value raised to the variable, and that's an exponential function. We now know how to do that. But what happens when we have a variable raised to another variable? This is something we have not yet done. And it doesn't just have to be a variable, it's just basically when we have some sort of function raised to the power of another function. Okay? So that's when logarithmic differentiation is going to be very helpful for us. So we're just going to jump straight in with this. And for our first example, we're going to look at y equals our most basic example of x to the x. So again, I see this and I know I'm going to use this approach because I have a function raised to another function as a power. So what we're going to do here is we're going to take the natural log of both sides. Okay, and the reason this is helpful for us is because it gets that exponent down. It undoes this. We're going to bring it down here in the next step, and that way we've taken care of the whole variable and the exponent problem. Now, you could also do like a log here, right? So you could also just do like log of y equals log of x to the x. The only reason you don't see a lot of people do this is because, as you've already seen, taking derivatives of logs with bases other than e just have a little bit extra work to do. So the fastest and most efficient base to pick is the natural base, or taking the natural log of both sides. Alright, so now that we've done that, we're just going to clean it up a little bit more by bringing that exponent of an x down front. Okay, that's just knowing our log properties there. And now we're ready to actually find the derivative. So here we're going to derive implicitly, which is what this whole kind of unit is focused around. So when we take the derivative of ln y, we get 1 over y, and remember we're going to use the chain rule here, so that'll be multiplied by dy dx. Okay, on the right side we've got the product rule happening. So we're going to have first times the derivative of the last plus last times derivative of the first. And we're going to clean up a little bit. So we've still got that 1 over y times dy dx. On the right side, well, we're just going to end up with, and we're multiplying by an x and dividing by an x. So these are simply going to cancel out and leave me with 1. And then ln x times 1 is just ln x. Okay, so the last step, and you're going to find this happens pretty much every time you do one of these problems, we have to get rid of 1 over y. And so the way we're going to do that is to simply multiply by y on both sides. And when you do that, make sure you put parentheses around. If your function has more than one term on the right, make sure to put those parentheses there. Okay, so this gets rid of that side, allowing us to solve for dy dx. And we really can only do one thing here. So we have the 1 plus ln x. And now instead of leaving a y as part of the derivative, I want it in terms of x if possible. I'm going to scroll back to the top and see what y actually equaled at the beginning, which is x to the x. So now I'm going to just plug that back in, times x to the x. And that will be our derivative in terms of x. Alright, let's try another. So for the second example, let's bring some trig in, because that always makes things better. So y equals sine x raised to the power of x. So again, I see a problem like this and I say, wait a minute, this is a function and so is the exponent. That's what I'm thinking. The easiest way to start this problem is to take the natural log on both sides, so I can get that x out of the exponent. Okay. Alright, so what we're going to do here, I'm just going to clean it up first before I actually start deriving by bringing down the exponent. So now we have x ln of sine of x. So we haven't done any deriving yet. This is just doing some manipulation with our algebra. So now I'm going to actually derive it. Derive implicitly. Okay. Oh, that was a horrible C. Alright, so the derivative of ln y is 1 over y times dy dx. Again, we're going to be using the product rule here, which you'll also find happens very frequently, because every time we bring down that exponent, we've got multiplication now. So first, times derivative of last, and be careful here. This is a chain rule, right? We've got a function inside of a function. So when we take the derivative of the last, we're going to get 1 over sine x, and then we're going to take the derivative of that inside function, which is cosine x. Plus last d first. Oh, that's right, forgot the ln. Hold on. Last. And then the derivative of the first is simply 1. Alright, let's clean this up. So I've got 1 over y times dy dx equals, alright, what's going on here? So we're going to get x cosine x on the top of our fraction. We got sine x in the denominator. And then the second piece, there's not much to do. We can just basically drop the 1. So we're going to have plus natural log of sine of x. Okay, so the last thing we're going to do here to simplify, anytime you see ratios with sine and cosine, they can be written in a simpler way. So cosine over sine, hopefully we recall, is actually going to be cotangent x. So that turns into x cotangent x because of that ratio right there. And then the plus ln of sine of x. Okay, and then I'm going to try to also go ahead, well, let's just do 2 separate steps. You can obviously combine some of these steps if you feel comfortable. Now I'm going to do that final part where I multiply by y on both sides so that I can solve for dy dx. And make sure when we do that, we're really multiplying this whole giant thing. So I'm going to get this going here. So x cotangent x plus natural log of sine of x, all multiplied by y, where y is sine of x to the x power. Alright, and that's as pretty as it's going to get. Alright, one last example. For this last one, we're going to look at the function y equals x to the ln x. Okay, we start these all the same way. So take the natural log of both sides. Just playing those games, trying to get things to look the way we want. So that gives me ln y equals, this is where it gets kind of weird. So we're bringing this down front, so we're actually going to end up with an ln x times an ln x. Alright, I would just leave it that way. I wouldn't try to find another way to write it, because we'll just use the product rule. It's not anything too bad. So now we'll derive both sides. Alright, I know you're really excited that all of these start the same way. Actually, it's kind of nice. So we always get that 1 over y times dy dx. Okay, so we're doing the product rule here. So first, ln x times the derivative of the last, which becomes 1 over x, plus last times derivative of first. So not surprisingly, we end up with something that repeats itself in a way. So we get 1 over y dy dx. Okay, so we can basically write this as a giant fraction, ln x over x plus ln x over x, which is very convenient because since they have the same denominator, we can combine them. So ln x plus ln x we'll simply write as 2 ln x over x. Okay, and that's equal to dy dx, and I now get to do that very fun last step of multiplying by y on both sides, and then actually substituting in what y is equal to. Alright, so we're going to get dy dx equals 2 ln x over x times x to the ln x. Okay, and something, right, every single time we get these answers, the original function shows up in the answer. So in that way, it's very similar to deriving regular exponential functions where it is its own derivative. It's just because we've got a function raised to a function, we also have a more complicated answer than that. But this will conclude our video on logarithmic differentiation. Make sure to let me know if you have any questions.